Okay, this chapter is on momentum and its conservation. So it's really actually pretty short for notes, but we'll do a couple labs and stuff. We'll do another lab with the air track, I think. So momentum, if you think about a train and a car, which one has more momentum? Why? Massive. Or what if you had two cars, one's going in town and one's going down the highway? Which one has more momentum? Because it has more speed. So it's all dependent on mass and speed. So the equation for momentum is down here at the bottom. That P thing is actually called rho. Rho. Rho equals mv, mass times volume. What? Okay, and then we also have impulse, which is the time frame which a force is applied. So we know the force is equal to mass times acceleration. Acceleration is velocity, change of velocity over change in time. So if we take force times the change in time, that gives us mass times the change in velocity. And mass times the change in velocity, what's mv? mv equals momentum, rho. So if we have m times the change in velocity, since an object, does its mass usually change? No, it just changes its speed. So in order to change momentum, we change the speed of an object. So mass times the change in speed is the change in momentum. And that's called impulse, yes. So the force applied in a given time interval is the impulse. So F delta T kind of looks like that equals MAV. But if this M delta V is the change in momentum, we can also say that the impulse is equal to the change in momentum also. So, do some problems. Pretty simple equations right there. It's thinking, it's trying to get the pen going here. There we go. Go with yellow. So a baseball of mass 0.14 kilograms is moving at 35 meters per second. What's the momentum of the baseball? How do we find it? Mass times velocity, which is 35. You said that's what?
4.9 kilograms.
Yep.
Is that what you always want to choose it to?
Yep. Kilogram meters per second. Okay, find the velocity at which a bowling ball that has a mass of 7.26 kilograms would have to have the same momentum as the baseball. So we're going to have 4.9 is equal to
0.67.
what'd you get?
0.67.
So does that make sense? Bowling ball is heavier, it has to have a slower speed to have the same momentum. So inversely proportional. Questions on that? Okay, a 0.144 kilogram baseball is pitched horizontally at 38 meters per second. Do you guys have this one? Yes. After it's hit by the bat, it moves horizontally at negative 38 meters per second. So what impulse did the bat deliver to the ball? What equation should we use?
Mass times change velocity over change in time.
mass times the change in velocity. Yes. Because our impulse is you can use either F delta T, but we don't know force or time. We can use M delta V, which we do know these, and you can also use just the change in momentum if you know the two momentum values. So we have 0.144. That's supposed to be kilograms. What's our change in velocity? We're going to use final minus initial, so we have a negative 38 minus 38.
Negative 76.
Negative
10 point. Okay, in this case, negatives, whoops. In this case, negative signs are going to show direction also, just like the velocity is showing a direction, right? So we're showing a direction. Meter per second. If the ball and bat were in contact for 8 seconds, what's the average force that the bat exerted on the ball?
So now we have to divide the change in time.
So now we can have, we know this is our impulse. We can take that as equal to force times the time. And we know the time, I guess, so let's change that to 0.8. So what's our force? And I dropped the negative just because we don't need a direction on this. 13.68 newtons. Because that's just direction. The average acceleration, what would we use? What equation? Force equals ma. So we have 13.68, right up here, so I have more room. 68 is equal to, we know the mass is 0.144 times A. So A is 95. There you go. That makes sense to have that high of an acceleration? Yeah, I think so. Questions on that problem? Oh. Mm-hmm. So 1,200 kilogram vehicle traveling at 94 kilometers per hour can be stopped in 21 seconds by gently applying the brakes. Should be stopped, not stopped. Stopped in 3.8 seconds if the driver slams on the brakes, or in 0.22 seconds if it hits a concrete wall.
Should have said hit a deer.
Yeah. What average force is exerted on the vehicle in each of these stops? Yep, okay, let's change 94 kilometers per hour into meters per second first. So in 1 kilometer, how many meters do we have? And then 1 hour has, do you guys know how many seconds? Yep, 3,600 seconds. Or you could go to minutes and seconds. Okay. So that's our change in speed, right? Because if in all the cases we're going from that speed to 0 because it's stopping. So our change in speed is 26 meters per second. Now what? Yes. What are we going to do with that?
We're going to take the mass times the velocity divided by
Okay, yes, we can have this all set up because we're looking for average force, so we can do this whole equation here, set them equal to each other since they both are impulse. They can be equal to each other. So the force is equal to the mass times our change in velocity is 26.1. And in the first case, the time is 21 seconds. So for the first one, 91? This is just newtons, isn't it? Because of a kilogram times a meters per second divided by a second. So we'll get a kilogram meters per second squared, which is the newton. Okay, so there's the first one. Now if it slams on the brakes, instead of 21 seconds, it's 3.8. So what's a force on this site in this case? 8,242. Wow, that's a lot of force there. Yeah, the next one, instead of 3.8, we have 0.22. And what do we get for this one? 363. There we go. That one is drastic. And so, 3.
There's 0.6. But get over it. You went to 95 on show 96.
Questions on this one? Is that the last one? No. Snowmobile. 2 more. Okay.
Snowmobile splatters a coyote. How much force?
Snowmobile. Mass of 250 kilograms. Constant force for 60 seconds. Snowmobile's initial velocity is 6 and its final is 28. What's its change in momentum? Now remember that change in momentum is equal to mass times the change in velocity. So we could take 250. What's our change in speed?
22.
That. Yeah, I just don't want to do all the exponent stuff.
Why did you put that into
Don't ask stupid questions.
That's not a stupid question.
What do we get?
Wait, what if you don't?
Okay. Magnitude of the force. We know that F delta T is equal to delta rho. And we already know delta rho, so our force will equal 5,500 over time 60. That's very good. Pretty simple equations to use, right? Compared to last chapter? Ooh, 91.6. Okay, how about you guys go through and figure these out? We'll compare answers. And remember, change in momentum would equal final minus initial, right? Wow, that looks horrible. Told you it's short. Test on Monday. Test on Monday.
Can we change it to May 1st?
What'd you guys get for cars mass?
1,600.
How about its initial momentum?
32,000.
You can also, I don't know, we'll have to check the book because the Newton second is the same units. It depends, I don't know. We'll have to see. What's the change in the car's momentum? Because it's going from 32,000, or it's going to stop. So it changes 32,000. And how long does it take? Because our change in momentum is equal to force times the change in time. We know the force, we know the change in momentum. So you get what? 50 seconds. 50 seconds is a long time to stop. There's no wall.
Well, it
It's a
says
deer.
line stops.
This is someone who really wants to save their brakes.
The real problem is how much time, lifetime brings
Yeah.
later on.
Okay. You guys need to work on page 870, 1 through 3. Three problems.